Alright, so in the previous video we learned how to solve second order linear homogeneous equations of constant coefficients. Now we're going to learn how to solve equations of order 87, or order 3, or order 9. We're going to actually learn to solve equations of arbitrarily high order as long as they're linear and constant coefficients. The method is very similar to the method that we learned for the second order. Let's see. So the algorithm is 3 parts. First, find the characteristic polynomial. There's one thing to, for example, I have this equation here, order 4, fourth derivative is the highest. The characteristic polynomial is a4 lambda to the 4 plus a3 lambda cubed plus a2 lambda squared plus a1 lambda plus a0. That's the characteristic polynomial. A mistake that many people make, and I'm warning you not to make it, people sometimes get x3, for example, minus x equals 0. People say, oh yeah, characteristic polynomial is lambda cubed minus lambda. No, it would be minus lambda if this were a dot, right, a derivative. But if there's nothing here, it's minus 1. Okay, so just watch for that mistake because it's pretty common. All right, so again, algorithm. Step 1, find the characteristic polynomial. Second, find the roots. And now, depending on the roots, the general solution will be the sum of different solutions. You have to add one solution per root, or one group of solutions per root, depending if it's a simple real root, a pair of simple complex conjugate roots, a multiple real root like double, triple, and so on, with multiplicity k. K is the number of times that the root appears, so if it's double, k is 2, if it's triple, k is 3, etc. Or a pair of multiple complex conjugate roots with multiplicity k. You can have, in the previous case, the highest you can go with real multiple roots was 2, because there's only 2 roots. It could be the same, so it could be multiplicity 2. And only one simple pair of complex conjugate roots, right? Because the degree of the polynomial was 2. But now the degree of the polynomial can be anything, and therefore you can have multiple complex roots as well. This will be very clear when we see examples. Don't worry, just follow what I'm saying, follow the recipe. If you find a simple real root, you just add a constant times the exponential of lambda t. Easy. If it's a pair of complex conjugate roots, then you add, that is alpha plus minus I theta, you add the exponential of alpha t, and then c1 cosine of theta t plus c2 cosine of c2 sine of theta t. These two things are exactly the same as we learned with the order 2 equations, all right? Because this can appear as well in the order 2 equation. Multiple real root lambda with multiplicity k. In the order 2 equation, the maximum that multiplicity could be was 2. So what you got was adding this, right? Remember? E to the lambda t times the polynomial c1 plus c2t. Now, the multiplicity here could be triple, quadruple, or n, k multiplicity. So if the multiplicity is k, you need to keep adding polynomial order starting from 0 and ending in k minus 1. So c1 plus c2t plus c3t squared plus c4t cubed, and so on and so forth until you get, if k is 52, that will be c52t to the 51. All right. Another thing that you can have is, this one is new, this one couldn't appear in the order 2, it can only appear when you have order 3 or higher, and in fact not order 3, order 4 or higher, order 3 cannot appear either. You can have a pair of multiple complex conjugate roots, alpha plus minus I theta, with multiplicity k. We will see examples where that appears, but if that's the case, what you need to do is very similar to what you did with the real ones, only that now you need to add a cosine and a sine. So you get the exponential of alpha t, same as when the multiplicity was 1. But now for the cosine, you need to multiply by a polynomial. Again, same as for the exponential. c1 plus c2t plus c3t cubed until you reach the multiplicity. t squared, until you reach the multiplicity, times the cosine, and then different constants here, d1, d2t, plus d3t squared, plus d4t cubed, until you reach dk t to the k minus 1, times the sine of theta t. So there are different constants, I call them d's and c's here. When I solve exercises, I would call these ones, imagine that the multiplicity was 3. I'll have c1, c2, c3 here. I could call this one c4, c5, c6. But because I have an indeterminate number, I decided to change the name to c and d. Those are names of constants, it's just a convention. So whether they're called c or d or consecutive numbers, the important thing is that the constants here are different from these ones. All right, so these are the rules. Take a picture, screen capture of these rules, and keep it, or write it down, and keep it handy for the examples that we're going to do. We're going to do about 9 examples, and I'm pretty sure it's going to be very clear when we see the examples. Just remember the rules, okay? Let's go see those examples. All right, let's do some examples. First, let's find the general solution of this equation here. Notice that y to this 4 with parentheses means the fourth derivative is the same as writing 1, 2, 3, 4 dots here, right? But this is, I'm not going to write 4 dots, I write a 4 in there. So 4 derivatives of y minus y equals 0. Okay, first of all, let's find the characteristic polynomial. So the characteristic polynomial is lambda to the 4 minus 1. Now, of course, don't make the mistake of saying minus lambda. This one is the one that would have minus lambda, but this is not what I am having here. I'm having nothing, so it's lambda to the 4 minus 1. This polynomial is easy to factorize in its roots. So this thing is lambda squared plus 1 times lambda minus plus 1 times lambda minus 1. All right, so the roots come, the roots of course, you get when you equate this to 0. Lambda squared plus 1, lambda plus 1, lambda minus 1 equals 0. Okay, so we get these 3 roots. So we get 4 roots. Lambda 1, this one is when this is 0, right? When lambda is equal to 0, so to 1, so lambda 1 is 1. Lambda 2 is minus 1. And lambda 3, this turns 0 when lambda is I or minus I. So lambda 3 and 4 are plus minus I. Okay, identifying the roots. This is a simple real root. This is also a simple real root. And this is a pair of simple complex conjugate roots. Remember, when we have complex conjugate root pairs, we have that we write lambda as alpha plus minus theta, plus minus I theta. In this case, that means that alpha is 0, no real part, and theta is 1. All right, so all that we need to do is apply the algorithm. Okay, let me write the solution y of x. I'm using x for the independent variable here. I mean, it could be t, and it will be t in the other exercises, and you want you to keep your diversity of open-mindedness with variables here. Anyway, so y of x would be equals, okay, I have 2 simple real roots. Every simple real root is an exponential. So I would get c1, I'm gonna write it fully in this first example. I will not write it fully in all the others, right? But this one will be lambda 1x plus c2 e to the lambda 2x, because 2 is also a simple root. And for the complex conjugate pair, I would have e to the alpha x times c3 cosine of theta x plus c4 sine of theta x. Right, if I substitute the values, it would be c1 e to the x, to the x plus c2 e to the minus x plus alpha is 0, so it's just c3 cosine of x, because theta is 1, plus c4 sine of x. And that's the solution. That is the solution to this equation. All right, the algorithm is going to be the same all the time. Let's do another. No, it didn't work. All right, so we have this equation. It's a 5th order equation, so 5th derivative plus 5 times 4th derivative plus 10 times 3rd derivative plus 10 times 2nd derivative plus 5 times 5 derivative plus the function equals 0. All right, let's write the characteristic polynomial. So let's write it here. So this is lambda to the 5 plus 5 times lambda to the 4 plus 10 times lambda cubed plus 10 times lambda squared plus 5 times lambda plus 1. Now, in general, finding the roots of a 5th order polynomial is difficult, but not this one. I mean, you're not going to have to do it by hand or being like knowing. There are techniques to do it, but computers do it very fast. And the focus of this course is not finding roots of polynomials, it's solving differential equations. So you can definitely and without shame use a computer to find the roots of this polynomial. It's very easy in this case. Look. 1, 5, 10, 10, 5, 1. Do you recognize the expansion of the monomial? This is actually lambda plus 1 to the 5th power. This is the expansion of the monomial. So we have one root, lambda equals minus 1, but it's multiplicity 5 root. So this thing roots, equating lambda plus 1 to the 5 equals 0, we find that we have lambda 1, 2, 3, 4, 5 is minus 1. So it's a multiple real root with multiplicity 5. All right, so if we remember the algorithm we saw right at the beginning of the video, we know that it is, let's take now t as the variable. Y of t would be equal to, first, exponential of lambda t, so exponential of minus t in this case, and then times a polynomial. And we start with c1 plus c2t plus c3 t squared plus c4 t cubed plus c5 t4. And there we go. You have your 5 independent solutions, 5 constants, and this is the solution to the equation. Not difficult, I would say. Let's do another. All right, so now we have this one. Third derivative minus the function equals 0. So the characteristic polynomial, it's easy. It's lambda cubed minus 1. Now, lambda cubed minus 1, it's a characteristic polynomial that we can write as the sum of these two factors. Lambda minus 1, lambda squared plus lambda plus 1. All right, wonderful. So that is something you can do eyeballing it, but you can also use a computer to find the roots, no problem. Let's find the roots. So the roots of that is when you equate lambda minus 1, lambda squared plus lambda plus 1 equals 0. There are two ways. Either lambda is equal to 1, that gives me my first root, lambda 1 equals 1. Or it could happen that lambda squared plus lambda plus 1 equals 0. When that's the case, we use the quadratic formula to get that lambda 2 and 3 is equal to minus 1 plus minus square root of b squared, which is 1, minus 4 times 1 times 1 divided by 2. Aha! So 2 and 3 are equal to minus 1/2 plus minus I square root of 3, square root of 3 divided by 2. So we have here we have a simple real root, and here we have a pair of simple complex conjugate roots. All right, so for this one we see that alpha is equal to minus 1/2 and theta is equal to root 3 divided by 2. Okay, let's apply the algorithm we have, and we find that y of t is equal to, remember, for the simple real root, we get c1 e to the lambda t, lambda is 1, so e to the t, e to the 1 times t, plus, now, a pair of complex conjugate real roots, that is e to the alpha t, alpha is minus 1/2, so minus t divided by 2, that multiplies c2 cosine of theta t, so root 3 divided by 2 times t, plus c3 multiplies the sine of root 3 divided by 2 times t, and that is the solution of this third order equation. Of course, third order, 3 independent solutions, this one, and this one, multiplied by the exponential. All right, okay, so far so good, I hope. Let's see another example. All right, so we're going to do this example. We have a 6th order derivative plus 3 times 4th order plus 3 times 2nd order plus the function. So let's write the characteristic polynomial is lambda to the 6 plus 3 times lambda to the 4 plus 3 times lambda squared plus 1. Now, this feels like a monomial again. 1, 3, 3, 1 is the second row of the monomial. So this monomial, the third row of the monomial, so this thing is actually lambda squared plus 1 to the power of 3. All right, so if we find the roots, we get lambda squared plus 1 equals 0. So you can tell that you have a pair of complex conjugate roots, with the 3 of course, but it's a triple pair. So you have one root 3 times and the complex conjugate 3 times. So lambda is equal to plus minus I, but all the 6 roots that there are come from here. So the plus I multiplicity 3, minus I multiplicity 3. So what we have here is a pair of multiple complex conjugate roots with multiplicity 3. All right, so again, complex conjugate, so we have alpha equals 1 and theta equals 0 and theta equals 1, right? Remember, lambda, when it's a complex one, we write as plus minus sine theta, and when we got it as plus minus sine, so alpha is 0, theta is 1. Now we write the solution. Let me write it first without substituting, and then I'll substitute because it's a bit more complicated than the other ones. So we have, remember, the exponential of alpha t, and that multiplies the polynomial c1 plus c2t plus c3t squared. That comes with the multiplicity 3, and then the cosine of theta, I'll write it like that, theta t, plus then c4 plus c5t plus c6t squared, the sine of theta t. All right, so this is exactly what you get in this case. All right, substituting the values of alpha and theta, we get finally the solution, which is alpha is 0, so this is a 1. So basically this is c1 plus c2t plus c3t squared, cosine of theta is 1, so cosine of t, plus c4 plus c5t plus c6t squared times the sine of t. And this is the solution in this case. All right, hopefully not too difficult. Notice that when I was giving you the theory, maybe I wrote D, D1, D2, D3 is the same, of course. I just give them consecutive number names. You cannot repeat the same constants, that's all. And you need to have 6 total constants because it's an order 6 one. Another example. Oops, it didn't work. Let's try now. Okay, another very similar one. Characteristic polynomial, lambda to the 4 plus 8 times lambda squared plus 16. Now this thing is again a monomial square, and the monomial square that we get here is lambda squared plus 4 squared. All right, so roots that can lambda squared plus 4 squared equate to 0. So we have a double root, but it's going to be a double pair of complex conjugate roots, because this is so lambda squared equals minus 4 means that lambda is equal to plus minus 2i. All right, so we got a pair of complex conjugate roots of multiplicity 2 in this case. So pair of complex conjugate roots, complex conjugate of multiple complex conjugate roots of multiplicity 2, right? Because of that. All right, so we just write the solution. Remember, again, alpha is equal 0, theta is equal 2 in this case. So it's very easy. I'll just write it directly. So you get a cosine and a sine times a polynomial because of the multiplicity. So you get the polynomial c1 plus c2t, order 2, so that's what you get. Multiplicity 2, that's what you get. Cosine of theta, that is 2, so cosine of 2t, plus c3 plus c4t, the sine of 2t, and that's it. That's the solution. Remember, there would be an exponential of alpha t, but alpha is 0. All right, let's see another. Cannot snap. Let's see if clapping works. Okay, let's see that example. This one is very similar to the previous one. The only difference with the previous one is that there's a minus instead of a plus. Okay, let's see what happens in this case. So we have the characteristic polynomial, lambda to the 4 minus 8 lambda squared plus 16, and that thing is lambda squared minus 4 squared. Well, this is simple. This thing actually factors as lambda minus 2 squared, lambda plus 2 squared. So clearly we have two roots, lambda equals 2, multiplicity 2, multiple, or I'm going to write double, real root, and 3, 4, minus 2, also a double real root. So two double real roots. Okay, so the solution, right, of x this time, is the exponential of lambda x, so exponential of 2x, times the polynomial with the multiplicity c1 plus c2t, plus the exponential of minus 2x, the other lambda, times c2 plus c3t. And that is the solution. All right. Let's do 3 more. I'm having troubles with because of the dust. All right, let's try again. Okay, so we have this example now. It's a little bit more involved. Let's first get the characteristic polynomial, lambda to the 4, minus 4 times lambda cubed, minus 8 times lambda squared, minus 8 lambda plus 4. This thing actually factors as lambda squared minus 2 lambda plus 2 squared. So we're going to have whatever roots come out of here, you're going to have multiplicity 2. Let's see what comes out of this. Let's use the quadratic formula. So lambda is equal to minus b, which is 2, plus minus, so divided by 2, the square root of 4 minus 4 times 2 minus 8. Okay? So what we get is 1 plus minus the square, that 2 comes in, if you want, well, it doesn't matter because it's 2 my I, right? This is 4 minus 8, which is minus 4, divided by 2 inside the root is 1, so it's the root of minus 1, so plus minus I. All right, wonderful. So we have a pair of double complex conjugate roots. How do I know it's double? Well, there's a 2 in there. Okay? If this 2 wasn't there, it would be simple. If it were a 3, it would be triple. All right, so let's apply the algorithm. Remember, in this case, alpha is 1, theta is 1. So what we get is that y of t is equal to e to the alpha t, so e to the t, that multiplies, and then we have a cosine and a sine with polynomials. Because it's double, so the polynomial is c1 plus c2t, cosine of theta t, so cosine of t, plus c1 plus c2, no, sorry, c3, c4t, multiplying the sine of t, because theta is 1. And that is the solution. All right, next one. All right, so let's deal with this example. This one is slightly more involved than others. So lambda to the 4 plus 4 times lambda cubed plus 10 times lambda squared plus 12 lambda plus 5. This actually factors as lambda plus 1, no, sorry, lambda plus 2 lambda, lambda squared plus 2 lambda plus 5, multiplying lambda plus 1 squared. Just looking at that, we immediately see that we have lambda equals minus 1 is a double real root from the square here. Lambda minus 1 cancels it. The other roots we find equating this to 0. So we get lambda squared plus 2 lambda plus 5 equals 0. That gives me that lambda is equal to minus 2 plus minus the square root of 4 minus 20 divided by 2, and that's easy because it's minus 1 plus minus. This is the square root of minus 16, so that's 4i divided by 2 is 2i. So we get here a pair of simple complex conjugate roots. All right, then for this one, alpha is minus 1, theta is 2. We can now write the solution, and the solution is going to be, as we have here, e. So we go first with the double real root, so let's just write here. Y of t is going to be, we have the exponential of lambda t, so the exponential of minus t, multiplying a polynomial, c1 plus c2t, because the multiplicity is 2, plus, and now we have the cosine and sine solutions. We have exponential of alpha t, alpha is minus 1, so minus t. And this now multiplies the cosine of 2 theta plus the sine of 2 theta. If you want, we can actually get common factor of the exponential of minus t, and then have c1 plus c2t plus, oh, I forgot, this is c3, this is c4, of course, plus c3 cosine 2 theta plus c4 sine 2 theta. And this is the solution. As it should be, we have 4 independent solutions because it's an order 4 equation, 4 constants. All right. Sorry about forgetting this constant here. Let's do the last example of the video. All right, so the last example is the 42th derivative of y equated to 0. We know what that's going to be. This is a problem we could integrate both sides many times. But let's do it with the expression, right? The characteristic polynomial is lambda to the 42, and the roots is roots. So it's all 0. The roots are 0 with multiplicity 42. All right, so remember, the general rule for a real, this is real, multiplicity 42, real root. So the rule is that y of t would be, let's write the root, exponential of lambda t, and then times c1 plus c2t plus all the way to c, in this case, well, k, t to the k minus 1. Okay, k is 42 in this case, so let me just write the solution. Y of t is e to the 0, which is 1, so this is just c1 plus c2t plus c3t squared plus all the way to c42t to the 41. And that's the solution. There are 42 terms in here, I just didn't write them. All right? Okay, so with that ends the video and the examples of order arbitrary linear equations that are homogeneous and constant coefficients. Now you know how to solve all of them. The next step would be to learn how to solve inhomogeneous equations. So that would be a matter for the next video. See you there.